Okay, let's let's go ahead and start. So this is going to be a very quick introduction to quantum information with a little bit of kind of teaser material for some of the talks that will take place on Friday. Okay, so quantum computing. First of all, the main point is that classical computing operates with bits. A bit can be either a 0 or a 1. And what makes quantum computing different is that it operates with these things called qubits, which are two-state quantum systems. They can be polarization states of a photon. They can be spin states of an electron. They can be energy levels of an atom. There are many different possibilities. We usually call one of the states 0 and one of the states 1. And the main difference between a classical and a quantum computer is that the quantum computer can actually exist in a superposition of the states 0 and 1, whereas a classical bit is either 0 or it's 1. Okay. Now, once you've got the quantum bits, you want to be able to do things with them, and that is done via quantum gates. And so here are three commonly appearing quantum gates. The first one, the sigma x, that's just in the Pauli matrix notation. That's a bit flip. So it takes a 0 and maps it onto a 1. So if I put in a 0 at the input, a 1 will come out. If I put in a 1 at the input, a 0 will come out. You can have gates like that on a classical computer as well. That would be a NOT gate on a classical computer. The sigma z gate is something that you cannot have on a classical computer. If you put in a 0, you get out the 0, fine. But if you put in the 1, it gets multiplied by a minus sign. So you don't have these phases on classical computers, whereas you do on quantum computers. So that is a major difference. Besides the 1 qubit gates, you also need 2 qubit gates, especially to produce entanglement. Okay, and the most common one is something called the C0 or controlled NOT gate. It has 2 inputs. It has a control input and a target input. And what happens is shown down there at the bottom. Basically, it's if the control is in the state 0, nothing happens to the target. And if the control is in the state 1, it flips the target. So if I put the control in a superposition, then what will happen is that the control and the target will become entangled. We'll have more to say about that in just a bit. And entanglement is something that you generally need to do take advantage of the quantum effects on a quantum computer. Okay, oops, there we go. Okay, so let's see, what can you do on a quantum computer that you can't do on a classical computer? So the first thing that was ever found, and it's probably the simplest illustration that you can come up with, is called Deutsches Problem, due to David Deutsch at Oxford University. So what you've got is you've got a black box, though in this case it's green, that evaluates a function. So the input is either 0 or 1. And if you the output is the value of the function on the input. So if you put in x, you get out f of x. And this is a so-called Boolean function. Boolean functions, f of x is always either 0 or 1. And this is about the simplest thing you can come up with, because it's a 1-bit input and a 1-bit output. Okay. Now, the idea here is that we don't know what f of x is. And we would like to determine whether it satisfies one of 2 possible properties. One possibility is that it's constant. In other words, f of 0 equals f of 1. The other possibility is that it's so-called balanced, that f of 0 does not equal f of 1. Okay. So the question is, how many times do I have to use the black box in order to figure that out? So it turns out that on a classical computer, you have to do it twice. You have to find out what is f of 0, and you have to find out what is f of 1, and then just look at them and see whether they're the same or not. But on a quantum computer, you can get away with just using the box once. And you can do that by taking advantage of the fact that you can put the input into a superposition state, and then if you make the correct kind of measurement, and you can then determine whether the function is balanced or constant with just one measurement, with just one use of the box. Okay, here, this is how it works. This is the quantum circuit. So it's a 2-qubit circuit. And so the first qubit goes in state 0, and the second qubit goes in this 1 over square root of 2, 0 minus 1, okay, the superposition state. And then we have these gates. So then the question is, what do the gates do? The first one is a so-called Hadamard Gate. What it does is it takes 0 and puts it into a superposition of 0 and 1, and it takes 1 and puts it into a different superposition of 0 and 1. Okay. Again, this is a kind of a gate that simply does not exist on a classical computer, okay, because there are no superpositions on a classical computer. Okay, so then we have to worry about this other gate, this F thing. So how does that work? Okay, so let's see what that does. So with it's called an F-controlled NOT gate. So if the input is X, 0 or 1 up here, and this thing down here is 0, what happens is that you get X0, which is the input, goes to X f of X. Okay, and I really should have put in what happens if you put in a 1 down here at the bottom. In that case, what happens is the X1 goes to X1 plus f of X, where the addition is modulo 2. So if you go back to the circuit and you start your qubits here, and then you look at what comes out at the end. Okay, so let's see what in fact does come out at the end. You get this big mess down here. Okay, so let's take a look at it. And so if okay, so the second qubit, essentially nothing happens to the second qubit. The second qubit does play a role, but it's the same at the output as it is in the input. So we're going to be measuring the first qubit, the one in the upper line, to actually see whether the function is constant or balanced. And so if I look at what comes out here, you'll notice that these first coefficient here, the one multiplying the 0 state, if f of 0 is equal to f of 1, that is going to be either plus 2 or minus 2, okay? On the other hand, the second coefficient is going to be equal to 0, if f of 0 equals f of 1. So that means that the function is constant. The first qubit will be in the state 0. Now, if the function is balanced, this first term, the minus 1 to the f of 0 plus minus 1 to the f of 1, will be 0, okay? Because one of those will be 0 and one of them will be 1. But the other term, the one where we have the difference, that will be either plus 2 or minus 2. So if the function is balanced, the first qubit will be in the state 1. So all I have to do is, at the output, measure the first qubit. If it's in the state 0, the function's constant. If it's in the state 1, the function is balanced. And you'll notice, going back to look at the circuit, there's only one use of the black box in that circuit, okay? So we've gotten away with just using one evaluation of the black box, and then we could figure out with certainty whether the function was balanced or constant. Okay, now to get to a more useful quantum algorithm, there is the Grover search algorithm, which is another black box algorithm. Again, we have input x going in and f of x coming out. Now, in this case, x is an n-digit binary number. Okay, so x is going to be represented by n qubits, not just one, like the previous one. F of x is still a Boolean function. In other words, it's either 0 or 1, but it's different from the last one. So f of x, in this case, it's 0 for all of the entries, all of the possible inputs except 1, okay? And for that special one, it is equal to 1. And the point is, we don't know what that special input is, and we would like to find it. Okay, so I'm calling that special input x0. So for this special input x0, f of x0 is equal to 1, but f of x, everything else is equal to 0. So how can I find x0? And how many times am I going to have to use the function box in order to find that? Well, classically, you would have to use it about, you'd probably have to evaluate about half the inputs, okay? So there are 2 to the n possible inputs, so you're probably going to have to evaluate, well, maybe 2 to the n minus 1 here instead of order 2 to the n, okay? You know, if you're unlucky, you might actually have to look at all of them. If you're really lucky, you might find it on the first try, but on average, you're going to have to try about half of them, okay? On a quantum computer, you only have to try the square root of the number of inputs. So in other words, 2 to the n over 2. So that is a quadratic speedup. So so for example, instead of if n is well, let's see, if n is 4, classically you'd probably have to try it about 8 times. Quantum mechanically, you'd have to try it 4. Okay. So it represents a quadratic speedup, and it's an extremely flexible algorithm. It can be used to do lots of other things. So the Grover algorithm is very often, or some variation of it, is a component of a lot of other quantum algorithms. Okay, so those are 2 quantum algorithms, one very simple, one very a bit more complicated and certainly a lot more useful. The one that really got people's attention was the Shor algorithm. I think it appeared in something like, what was it, 1994 or 5, something like that, okay? So, I mean, quantum computing had been a rather small field. People looking, it kind of started in the 1980s. People were looking at, it really kind of started with, say, people like Rolf Landauer and Charlie Bennett at IBM. The idea being that a computer is a physical device. So physics should have something to say about what a computer can do. And that got them looking at the possible limitations on that physics would impose on computation. And one of the ones they were thinking about was quantum mechanics. And then David Deutsch came along and showed that quantum mechanics is actually an advantage. Okay, and then things kind of, it was kind of a curiosity. And then when Shor came out with his algorithm, all of a sudden people got really interested because it has to do with code breaking and things like that. And government agencies like the US National Security Agency got very, very interested. Okay, so what is it? So you're given an n-digit number and you want to find its prime factors. So any integer can be uniquely factored into prime numbers. Okay, and so then the question is, how many steps does the computer have to go through in order to do this factorization? And the best known classical algorithm there is, roughly 2 to the n to the 1/3, where Shor's algorithm will do it in order n³ steps. So that represents an exponential speedup over what's possible classically. And the reason that that's so interesting is to especially people who have to worry about cryptography, is that most codes are based on the fact that it is hard to factor numbers into their prime factors. So you got a big number, it's very difficult to find the prime factors of that number. If it becomes easy, all of a sudden, a lot of the codes in use become useless. Okay, so that is what really got people's attention. And I'm not going to go into any details on Shor's algorithm because it's kind of complicated. So anyway, we'll leave that particular one there. Now, one of the talks at the symposium is going to be on something called indefinite causal order. And one of those, a part of that is something called the quantum switch. So this was based on work done by Giulio Hirabella and Czeslaw Bruckner. So Czeslaw is going to be the one giving the talk. He'll actually be giving the talk from Vienna because he's a professor at the University of Vienna. Now, this is a much more complicated quantum circuit than we've seen before. So what it does is the following. the point is it creates a superposition of operations happening in different orders. So we have two quantum gates. One of them does, I'm going to call it an operation U sub A, and the other one does an operation U sub B. And what we would like to do is we would like to create a superposition of B happening first and then A, or A happening first and then B. So, and it turns out that being able to do this kind of thing is actually quite useful, and it has some algorithmic applications. And Chaslav is going to be telling us about that kind of thing on Friday. So, so this big thing here, I'm not going to go through it in detail, so what you've got is you've got your input state psi is in the middle. You put plus x up on top. That kind of controls some of the operations, and you put in 0 down here because you need an extra qubit to sort of do what you want to do. These S things are called controlled swap gates. So if the top line is the control, if it's 0, nothing happens. If it's 1, it swaps the states of the two qubits. So the circuit consists of 4 controlled swap gates. Then I have UA, UB, and then UA again. Okay. You can show that there's no circuit that will do this if you just have UA and UB. You need at least to have one of those. You have to have one of those gates twice. And the X, that's a bit flip. That's our sigma X gate that we looked at earlier in the talk. And the output of this thing, you can see it down here, is it's if the upper qubit is in the state 1, A is applied before B. If the upper state is in the state 0, B is applied before A. So you get a superposition of different causal orders of the operations in the circuit. Okay, so as I said, you're going to hear a lot more about this on Friday. Okay, now quantum information has some unusual properties. So quantum information is simply information represented in terms of qubits. And one of them is that you cannot clone it. Quantum information cannot be perfectly cloned. So a device like I'm showing here is impossible. Okay, so you put in a qubit in the state psi, and you put in a qubit in some reference state. Okay, this is like, so this is the thing the psi is the thing you want to copy. The 0 is the blank piece of paper in the copy machine. And what you'd like to get out is 2 copies of psi. And it turns out that there's this thing called the no cloning theorem, which shows that this operation is impossible. Okay, the way it was discovered is kind of amusing. There's a book called How the Hippies Saved Physics, which, despite the title, is excellent. And it's about a bunch of sort of crazy people, all of whom had solid PhDs in physics, but they sort of got caught up in the all kinds of weird stuff in San Francisco on the West Coast. And they didn't have jobs in physics. That was when the physics job market collapsed. So they formed this thing called the Fundamental Physics Group, which met every Friday at a conference room at the Lawrence Berkeley Laboratory. And one of them, a guy by the name of Nick Herbert, came up with a scheme that he claimed would allow you to communicate faster than light. That's not allowed by relativity. So clearly something had to be wrong. And his device depended on the ability to clone qubits. And so some people had a look at this, including Wojciech Zurek and Bill Wooders, and they realized that was the problem, that Herbert's assumption that you could clone qubits was the defect in his scheme. Let me just see what the chat here is. Okay. Okay, thanks, going. Yeah, just, I mean, I played an extremely tiny part in this whole story because the paper, I was a postdoc at the time, the paper was sent to the person for whom I was a postdoc. He didn't want to do it. So he dropped it on my desk and sort of said, you deal with this. And so I took a look at it. Now, I mean, I didn't, this was a case of knowing too much. If I hadn't known anything about how quantum amplifiers work, maybe I would have discovered the no cloning theorem, but I didn't. Okay, but what happened was I did know how quantum amplifiers work, and I knew that amplifiers always add noise, and so I strongly suspected that since the scheme that was being proposed was noiseless, the cloning scheme, that had to be wrong, and that if you did things properly and used a real proper model for an amplifier, the whole effect would go away, and then I had other things to do, and so I just sort of said, reject this paper and get it off my desk. Okay, anyway. Wooters and Zurich didn't know about quantum amplifiers, so they had to think about things from the ground up, and that's how they found the no cloning theorem. So okay, so let's move on. Now, another thing that is very important is, okay, yes, Alex, thanks for the comment. Okay, yeah. Sometimes it pays not to know quite so much. Actually, by the way, some other people, actually, some of the other referees, one of the other referees was a guy in Italy. I can't remember his name off the top of my head. Also said to reject the paper, and in his referee report, he proved the no cloning theorem. And then he spent the rest of his life kicking himself for not having published it. So that was another case of where someone, I mean, he actually discovered it, and he should have published it, but he didn't, and he was really sorry that he didn't. Okay, entanglement. So a 2-qubit state is not entangled, or we call it separable, if it's in the form of a product. Okay. And this kind of state can be prepared by two parties, which we're going to call Alice and Bob, because that's what everybody calls them, each in their own laboratory. Alice prepares psi, Bob prepares phi, end of story. Okay. Now, any state that is not of product form is called entangled. Any pure state is called entangled. Okay. And in order to prepare an entangled state, Alice and Bob have to exchange qubits. Okay, they can't do it. I think, let me just take a quick forward look here. I think it's, yeah, okay. Let me go back. Okay, so they can't do it by what's called LOCC, local operations and classical communication. So in other words, if Alice and Bob start with 2 qubits and they're not entangled, and the then and they want to entangle them, they cannot do it by just doing operations in their own laboratories and then talking on the telephone to each other. Okay, so that's what LOCC really means. They actually have to exchange qubits. All right, so classical communication won't do it. They have to exchange qubits to create an entangled state. A standard example of an entangled state is the one shown here, a singlet state for a single for 2 qubits. The way this thing, if Alice and Bob were to measure this thing, it would work in the following way. Okay, so they each have a probability of getting 0 or 1, but whatever Alice gets, Bob will get the opposite. Okay, so there's strong correlations between the measurement results that Alice and Bob get. Individually, Alice and Bob get totally random results, but if Alice gets 0, Bob will get 1, and vice versa. Okay, so entangled states can produce strong correlations, and we already said that this cannot be created from local operations and classical communication. Okay, and entanglement is a resource that can be used for various quantum communication tasks. Okay, so since we're calling it a resource, let's talk about these things called quantum resource theories, and that will enter into one of the other talks that will be given on Friday by Iman Marvian, who's on the faculty at Duke University. So a quantum resource theory needs 3 things. It needs a resource. Now I'm going to use the example of entanglement here, because that was really the first quantum resource theory. So in the case of the resource theory of entanglement, the resource is entanglement. It also needs operations that do not produce the resource. And in this case, it is the LOCC operations, the local operations and classical communication. And then it needs some way of measuring the resource. Now, in the case of entanglement, at least pure state entanglement, the way the standard measure for entanglement is the von Neumann entropy of the reduced density matrix of one of the qubits. Okay, so what do? You take the state, the 2 qubit state, AB, okay, you trace out one of the qubits, okay, that leaves you with a state of just 1 qubit, and then you take minus trace rho log rho, which is the von Neumann entropy of that 1 qubit density matrix, and it turns out that that's a real good measure of entanglement. Okay, so that would be the resource measure in that case. There have been a bunch of quantum resource theories proposed recently. The first one after entanglement was really something called coherence. Okay, and the resource theory of coherence. And I'm not quite sure what Iman's going to be talking about on Friday, but I'm sure it's going to be interesting. And I know resource theories play a role in it. Okay, so let's talk briefly about quantum communication. And this is, for example, why you can think of entanglement as a resource, because it allows you to do some things that you wouldn't otherwise be able to do. So in this case, Alice has a qubit, and we're going to call it psi, okay? And then she and Bob share an entangled state. So she's got one half of it and Bob's got the other half, and it is our singlet state, okay? Now, what Alice wants to do is she wants to transfer the state of her qubit, psi, onto Bob's qubit, okay? Now, of course, she could try measuring it and then sending Bob some classical information, but that's not going to work because that you can't determine the state of a quantum system by just one measurement. And once you've measured it, you're going to ruin it. So you have to come up with something more clever. So it turns out that what Alice should do is she should take her 2 qubits, okay, the one from the entangled state and the one that she wants to transmit, measure them in this so-called Bell basis, which is an entangled basis, okay, and then tell Bob what her result was. Her result is going to be one of these 4 states: phi plus or phi minus, psi plus or psi minus. So she simply tells Bob which of those results she got. And then what happens is that Bob can perform some operations. Okay, so she measures 2 particles, she sends the result to Bob, and then Bob performs some operations on his particle that depend on the result of Alice's measurement. And after they're through with all of this, Bob's particle will be in the state psi, okay? And of course, we have to be a little careful here because we just mentioned the no cloning theorem. So if Bob's qubit is in the state psi, that means that Alice's qubit is definitely not anymore. And so it turns out all information about this original state psi on Alice's side is completely gone. It's all been transferred from Alice to Bob, and there's no trace of it left on Alice's side. Okay. Now, you can also use quantum information to look at some very fundamental questions. And this one, there are going to be 2 talks on this type of subject. One by Jarek Korbich from the Institute of Theoretical Physics in Warsaw, and another by Jess Riedel from the NTT Corporation offices out in California. Okay, so what's the fundamental question? Okay, now when quantum mechanics was first developed, the idea was that there was a split. Okay, so you treated the small system like an atom or whatever in terms of quantum mechanics, but on the measuring device, everything was supposed to be classical, and there was supposed to be some kind of a dividing line between the two, and it even had a name. It was called the Heisenberg cut. And the Heisenberg, you could sort of put the Heisenberg cut pretty much wherever you wanted. It didn't seem to make too terribly much difference. But the idea was that you had a classical big world and a quantum small world, and that's the way things were. Well, people are not assuming that anymore. People are saying, okay, quantum mechanics is the basic theory, so it really should be quantum mechanics all the way up. So, everything should be described by quantum mechanics. Now, some of the older physicists didn't like this idea at all. I don't know how many of you have heard of Freeman Dyson. Of course, I think Freeman Dyson simply liked to disagree with everybody. He was brilliant, by the way. He was responsible for the formulation of quantum electrodynamics. He sort of was the only person who could understand both Schwinger and Feynman and then combine their two theories into something that everybody else could understand. Anyway, but he was very much of the view of these sort of two worlds, classical world and quantum world, and he didn't much like this idea that it's quantum mechanics all the way up. So anyway, the talks you're going to hear on Friday both assume that it's quantum mechanics all the way up. And so then the question is, well, how in the world do we get a classical looking world out of these crazy quantum rules? And so let me just give you some partial answers here. So one thing we don't see in our classical world is we don't see superpositions as a general rule. I mean, the standard one, of course, is the Schrodinger's cat. Now, since I've got 3 cats in this house and I'm very fond of cats, I'm not going to talk about dead cats, but I'm going to talk about awake and sleeping cats, okay? So you can't have a superposition of an awake cat and a sleeping cat. It's one or the other, okay? And of course, Schrodinger had an argument that he claimed could produce a superposition like that, which he considered completely absurd. And Schrodinger, by the way, actually never really believed in the standard interpretation of quantum mechanics, despite the fact that he was one of the people who really made huge contributions to it. Okay, so somehow you have to get rid of crazy superpositions. This can be done via something called decoherence. And the basic idea is that you don't really have isolated systems. Systems interact with their environments and they become entangled with their environments. And this can actually get rid of these kind of crazy superpositions. Well, let's just do a very simple example and see how that can happen. So I'm going to use that controlled NOT gate. And I didn't introduce this symbol before, but this is the circuit symbol for a controlled NOT gate. And that's going to be my interaction between the environment and the system. So here's my system. That's the first qubit. And I'm going to call the second qubit my environment. Okay. And so what happens when I put it through the controlled NOT gate? So the system input is some superposition of 0 and 1. Okay. And then what happens is it gets entangled with the environment qubit. And so if I then trace out the environment, because usually we can't, if I have some quantum system and it's interacting with the environment, I only really have access to the system. I don't have access to the environment. The information that is sort of flowed into the environment is, from my point of view, lost, and I really don't have access to it. So if I just look at the system qubit, it looks like an incoherent superposition. In other words, the system is either in the state 0 with some probability alpha squared, or it's in the state 1 with some probability beta squared, but there are no weird superpositions, no interference effects between the 0 and the 1 are possible at this point, because I've entangled with the environment, I don't have access to the environment, and so the phase information between 0 and 1 is completely destroyed, okay? So decoherence can help you get rid of some of these crazy superpositions, like superposition between a sleeping cat and an awake cat. Okay. So now, this is part of, now decoherence was not discovered by Wojciech Zurek. It was discovered by Hans-Dieter Zeh. And he emphasized the importance of it. But it's been incorporated by Wojciech Zurek, who's at Los Alamos Laboratory, into something he calls the quantum Darwinism. So it's really kind of a research program, and Zurek has been driving it for quite a few years. He is, by the way, one half of the team that discovered the no cloning theorem. Okay. So the first thing is, okay, so I was talking about superpositions. Well, superpositions of what? I have to really kind of specify a basis if I'm going to be talking about no superpositions, okay? So there's going to be some special basis And what the interaction with the environment is going to do is it's going to somehow destroy superpositions of things in that basis. Okay. So the idea is that this special basis, and this basis is stable under interaction with the environment, is called the pointer basis. Okay. As essentially the interactions of the system with the environment will destroy superpositions of states in the pointer basis. So I'll just get the basically incoherent superpositions of the pointer basis out. And again, you're going to hear a lot more about this on Friday. By the way it's going to work on Friday is that the first talk on this kind of stuff by Jarek Korbich, he and his co-workers have kind of a different approach to this from Zurich. What's it called? Okay, I can't remember at the moment. Anyway, so you'll hear about that approach. And then Jess Riedel, the second talk in the afternoon on this subject, has actually worked with Zurich. But he also adds some of his own extra elements to this research program. So you're going to hear about two different approaches to this business about sort of recovering a classical world from quantum mechanics. Okay, so back to the quantum Darwinism. So one aspect of the quantum Darwinism is decoherence in the pointer basis. The other aspect, which Zurich has emphasized more recently, is the spreading of information about the system throughout the environment. So his idea is that different fragments of the environment contain the same information about the system. Okay, so what this guarantees is that different observers will all have access to the same information about the system. So different observers will all see the same thing, okay, when they start performing measurements. And there's an error in the second equation here. So you can sort of think of it in the following way. My pointer basis is 0 and 1. After interaction with the environment, 0 goes to 0 with a bunch of environmental fragments which are identical, which all carry the same information about the state 0. 1 goes to, that should be a 1 there, not a 0. Sorry. And fragments that contain information about the state 1. So all of these, all the E0s are identical and all the E1s are identical. This does not violate the no cloning theorem. You can clone states that are orthogonal. Okay, you can't clone. You can build a device that will clone 0 and 1, but then it won't clone superpositions of 0 and 1. So this is perfectly consistent with the no cloning theorem. So the second aspect of the quantum Darwinism program is this business about copying information about the system state into the environment and having being spread among many different pieces to which many different observers have access. So again, you will be hearing a lot more about this on Friday. Okay, now, now sometimes, well, in fact, in many cases, decoherence is a real nuisance. For example, if you're building a quantum computer, you really don't want decoherence operating on your quantum computer, because what that does is it destroys all the quantum effects. Okay. So somehow you want to be able to handle, basically get rid of decoherence. Okay, so how can you do that? So errors invariably arise due to interaction with the environment. Okay, we've kind of seen how that happened just in the previous few transparencies here. So we want to be able to correct them without disturbing the quantum information. Now that's kind of tricky, because to detect an error, you have to measure it. And measuring something usually, measuring a system usually changes its state. Right? And that we don't want. It also changes the state in an uncontrollable way. So that we definitely don't want to do. So somehow we're going to have to measure the state, but we're going to have to do it in a clever way so that we don't screw up the state in the process. So how does that work? So some people among them, actually, I guess the person who came up with the first quantum error correcting code was in fact Peter Shor again. Okay, obviously a very smart guy. So now there are a whole bunch of different quantum error correcting codes that you can choose from. So let me just give a very simple explanation for how one of them can correct an error. Okay, so take a simple example. So we've got the following state. We've got alpha 0 plus beta 1, and we would like to protect that state from a bit flip error. In other words, so if 0 goes to 1 and 1 goes to 0, we want to, and we end up with the state alpha 1 plus beta 0, we want to be able to correct that kind of an error, okay? So what we're going to do is we're going to encode 0 into 0, 0, 0. So we're going to encode 1 qubit into 3 qubits, all right? So 0 is going to get encoded into 0, 0, 0, and 1 is going to get encoded into 1, 1, 1, okay? And so our state would then become, hang on 1 second, alpha 0, 0 plus 1, 1, 1. Carol, can you turn that down? Okay, sorry. And so what we want to be able to do is if one of those qubits flips, we want to be able to fix it, okay? So let's see how that works. So what we're going to do is we're going to measure this state using sigma z operators, okay? So remember the sigma z maps 0 to 0, and it maps the 1 state to minus the 1 state, okay? Now, the advantage, the nice thing here is that this state, both 0, 0, 0 and 1, 1, 1, and actually in the whole superposition, is in fact an eigenstate of these two operators. So Z1 means I'm going to measure sigma z on the first qubit, Z2 means I'm going to measure it on the second qubit, and Z3 means I'm going to measure it on the third qubit, okay? So I'm going to measure Z1, Z2, and Z2, Z3 on the state, and the fact that this state is an eigenstate of these operators means that I'm not going to change the state in doing so, okay? So now, so suppose the first qubit flipped. Okay, so going back, so suppose instead of alpha 0, 0, 0 plus beta 1, 1, 1, I had alpha 1, 0, 0 plus beta 0, 1, 1. Okay, so then what's going to happen with the Z1, Z2 is that I will get, that will be, this thing will be an eigenstate of that operator with an eigenvalue of -1, but it'll be an eigenstate of Z2, Z3 with an eigenvalue of +1, okay? So now, if the second qubit flips, it's going to be an eigenstate of both of those operators with eigenvalue -1. And if the third bit flips, it's going to be an eigenstate of Z1, Z2 with +1 and Z2, Z3 with -1. So you can see by looking at the measurement results I get, I can tell which of the qubits flipped, okay? And then I can go in and correct it. And since these measurements don't disturb the state, I will have preserved the quantum information. So we can find out which bit flips without disturbing the state, flip it back to correct the error, and we have eliminated the effect of the bit flip. Okay. And now this is just a very simple example. And what you of course need to show is that you can eliminate all kind of decoherence errors on a certain number of qubits with a quantum error correcting code, and that takes a lot more work, but it can be done. And it, in fact, is I think there have even been some experiments at this point that show that you can do it. Okay, now so far we've been talking about the theory. So where do things stand in terms of experiments? So you physical realization of qubits, you can use photons, you can do neutral atoms usually if you're doing neutral atoms, you're doing arrays of neutral atoms, sort of trapped by light. You could also do trapped ions, ions trapped by electromagnetic fields, superconducting qubits. I think that one, I think it's quantum dots. Okay, so anyway, there are a number of different possibilities. The ones that have been developed so far to the largest extent are the trapped ions and the superconducting qubits. So this thing on the left here, that is a chip with a line of ion traps in it, okay? And that thing on the right is a bunch of superconducting qubits, which has to be held at a very, very low temperature. the superconducting qubits, those are being pursued by a number of people, in particular the groups at Google and IBM are working very hard using the superconducting qubits. The trapped ion qubits, the main company there is actually a startup. It's called IonQ, and it was formed by a guy by the name of Chris Monroe, who was until very recently at the University of Maryland. And he now has taken his whole operation and moved it down to Duke University in North Carolina. So both of these things have gotten up to the size of about between 50 and 100 qubits, and have kind of shown that you can perform, you can actually perform these quantum operations and get some kind of results out. So that is the status of the sort of the quantum computing. What about quantum communication? Well, probably the most spectacular version there. Let's see. Let me just check the chat because I'll make sure that. How about? Oh, okay. Yeah. Okay, Jonathan, you're ahead of me. Yes, Honeywell's quantum computer. I think the Honeywell. I think the Honeywell quantum computer. I believe that's a trapped ion machine. I don't know a lot about it. But I think I read recently that it's a trapped ion machine. So I don't know how theirs compares to the IonQ ones. Yes, Honeywell is trapped. Yeah, I thought so. So yeah, as to how theirs compares to IonQ, I don't know. And I think I read recently that IonQ is the first quantum information startup to be going public. In other words, the idea is that they'll be selling shares of stock, I guess. Okay. No comment about whether it'd be a good idea to buy it or not. I have no idea. Now, the state of the art in quantum communication is these satellites, or this satellite singular. So in 2016, China launched this satellite. Jianwei Pan is kind of the person behind this in China. He is kind of the big guru of quantum information in China. What the satellite does is it transmits entangled states that can be used for quantum communication. So it sends half of the entangled state into one place and half of the entangled state to the other. And then you can use it to do, for example, quantum cryptography, which is something I haven't really talked about, but you can also use quantum information to send secret messages. I believe this satellite was used to actually send encrypted messages between Vienna and Beijing. So that is kind of state of the art in terms of quantum communication now. You can, if you want to send quantum communication over fibers, at the moment there's a limitation because I mentioned that if you have quantum amplifiers, they always add noise to the signal. In a fiber, typically what happens is after about 100 kilometers, in a standard fiber, if it's you're sending a classical signal, you have an amplifier in there, you amplify the signal. If you want to send quantum information via a fiber, the amplifier is going to kill the quantum effects. So at the moment, you can only send quantum information via a fiber, something on the order of 100 kilometers. People are working on a thing called the quantum repeater, which uses entanglement to sort of get around the problem of the noisy amplifier. But no one really has an operational quantum repeater yet. Okay. Okay. Okay, so where do things stand now? Well, a lot of governments have gotten involved in this stuff. I mean, Europe has a big quantum technology flagship. The US has a national quantum initiative. And the funding agencies here tend to be very interested in supporting quantum information. China has put a ton of money into it. Nobody really knows how much. And as you can see from the satellite, they've really accomplished a lot. Okay, it's a very large effort. And they've built a huge $10 billion National Laboratory for Quantum Information in Hefei at the University of Science and Technology of China. But that's only part of their effort. Nobody really knows, again, how much the Chinese government has put into quantum information, except that it's a lot. Private companies in the US, it's IBM, Google, Microsoft. Those all have major quantum computing, and also Honeywell now. And there are a bunch of startups. IonQ is probably the one that's most developed, but it's by no means the only one. I think Berkeley, California has like 3 or 4 quantum computing startups at this point. And they tend to be using different platforms. So as I mentioned, the IonQ is using trapped ions, but there are also people looking at optical qubits, using photons as qubits to actually do not just communication, but also quantum computation. Actually in Jianwei Pan again, he and his group, they constructed an optical quantum computing thing to do something called boson sampling, which is something which is on good grounds assumed to be difficult to do classically. And they set up a quantum system to do it, and they claim that they have achieved something called quantum supremacy, which is they achieved a task with a quantum system that would have taken a classical computer some ungodly amount of time to actually do. Okay, these claims are usually disputed, so I'm waiting for the experts on that kind of stuff to weigh in. So the immediate goal in the field is to demonstrate, as I said, quantum supremacy, and Google has claimed that they have done it with a superconducting qubit quantum computer. Jianwei Pan and his group claim that they have done it using an optical computer. Theirs is a very, very, very much a special purpose computer. It was designed to do boson sampling, and that's it. Okay, very well, quantum supremacy may have been demonstrated. Again, I'm waiting for the experts. For this kind of thing, you want to hear from a computer scientist. Okay. So the idea is to build special purpose non-error corrected quantum computers that can perform a task that is beyond the capability of a classical computer, and that's exactly what the boson sampling thing does. So current quantum computers operate with, well, tens of qubits, 50 to 100 at this point. Our current situation has been termed by John Preskill of Caltech the NISQ era. That stands for noisy intermediate scale quantum. So that basically means you've got like 100 noisy qubits. And then the idea is to try to find out, is there anything useful you can do with a quantum computer that has 100 noisy qubits? And that is an open question. Nobody's really come up with anything really good so far. But there are plenty of people working on it now. And in order to build an error-corrected quantum computer that will actually be able to do, say, a Shor's algorithm or something. Well, I said hundreds of thousands here, but it's probably more like millions of qubits to make a universal quantum computer. And so we're still very far from that, but it still very well may be possible to do something interesting even at the sort of NISQ level, but we have to see. Okay. And so to conclude, how is it all going to turn out? Well, here are famous actors, Bob and Alice. Then all I can say is tune in 10 years and we'll see where things stand. Progress has been a lot more rapid than certainly I and most other people thought. And you have to hand it to the experimentalists. They've done a fantastic job, and we'll see what more they can do. Okay. So that's it from me. Does anybody have any questions? I think how many people we got? Oh, we've got a small enough number of people. If you have a question, just unmute yourself and go ahead and ask. Okay, the LOC, it's not LOCC. It's not really an axiom. It's a provable result, and it's really a consequence of quantum mechanics. That yeah, you can show that if you start out with an unentangled state, and all you have available are local operations and classical communication, you cannot create entanglement. So you can view it as a theorem, for example. So you can basically prove that start out with no entanglement, have only LOCC operations available, then you cannot create entanglement. Okay. What sort of research is being done in your lab regarding quantum information? Okay, I'm a theorist, so I don't have a lab. So what kind of stuff are we doing? We are doing, well, let me mention two projects, okay? We're working with a group at the Army Research Lab on what's called entanglement swapping. Entanglement swapping is the basis for building a quantum repeater. And so the military is very interested, or actually a lot of people are very interested in building a quantum repeater. This is the thing that will allow you to send quantum information longer distances. Because people are starting to talk about something called the quantum internet. Okay, don't ask me what it is. I'm not sure anybody really knows what it is, but somehow the idea is you're going to want to have a lot of entangled states that you can use to do teleportation. And in order to do that, you're going to need a quantum repeater, which means you really have to look at all the possibilities for this thing called entanglement swapping. So what entanglement swapping allows you to do is I've got two entangled states. Okay, so I've got, let's say we've got Alice, Bob, and Charlie. Okay, so I have one entangled state that's shared between Alice and Bob, and I have a second one that's shared between Bob and Charlie. And what I want to do is I want to take Bob out of the picture and just have a big entangled state that is between Alice and Charlie. So what entanglement swapping allows you to do is Charlie can do some measurements on his particles, because he has half of each entangled state. So he does a measurement there. He communicates his results to Alice and Charlie. And by the time they're done, Alice and Charlie have an entangled state. Okay. Can all quantum, okay, let me, again, before I get to that question, okay, now I'm glad people are asking questions, great, okay. Okay, so anyway, the idea is we want to gain a better understanding of entanglement swapping because this will allow quantum communication networks. Okay, so that's with the people at the Army Research Lab. We're also working on stuff having to do with wave particle duality. How do you quantify wave particle duality, making use of some of the ideas from this quantum resource theory of coherence, okay? And so that's been kind of an ongoing project with myself, Professor Bergu, who's also here at CUNY, and Emilio Bagan, who's at the Autonomous University in Barcelona. Okay. Okay, so could all problems be solved with a quantum switch? Certainly not all quantum problems can be solved with a quantum switch, but some can be. Okay, so it does allow you to do some things that you wouldn't be able to do without it. So again, I am not an expert on the quantum switch, but Chaslav is. And so tune in for the first lecture on Friday. Another thing, let me just mention about that. On the website for this workshop, there's a link to an article from Quanta magazine. I don't know how many of you are familiar with it. Quanta magazine is put out by the Simons Foundation. It's devoted to different fields of science, physics, mathematics, computer science, I think that's it, and biology. There was an article in Quanta magazine about this sort of indefinite causal order and quantum switch, and one of the people they talked to was Chaslav. Okay, are there any significant problems a la quantum Darwinism for explaining how class? Yeah, it's not finished. The whole quantum Darwinism thing, it's not done yet. It's an ongoing project, and the I wish I could remember what the this other approach is called. Oh, blast it, something or other structures. Anyway, I'm sorry. So anyway, you're going to hear about several different approaches, and the problems are by no means completely solved. Okay, this is very much ongoing research. And I think by listening to those two talks, you'll have a pretty good idea of where things stand. Anyway, so yeah, this whole quantum classical business, there's still a lot to be learned. Okay, any more questions? Okay. Okay. So I think what I'll do here is I guess we'll call it quits, and then see you on Friday.